We are still working through chapter 2 here. If you want to get your notebook set up, we are working on chapter 2, section 5, perpendicular lines. Before we get started with our new stuff, I've got 2 problems for you to try out and solve for our value of x. Think about what we learned about vertical angles in class yesterday. Hopefully you remembered that vertical angles are congruent, so to solve these both, you would set up equal equations. So 8x plus 207 equals 6x plus 185. And for my second one on the right, I would have 2x plus 62 equals 5x plus 38. The other way you knew these angles are congruent are the arches that mark our congruent angles. Okay. So hopefully you did okay on both of those, but I'm going to get us started with our new notes on perpendicular lines. And hopefully, I imagine a lot of you have heard about perpendicular lines before, probably in algebra, and you might remember that perpendicular lines have opposite slopes. But what we need to know for this year is that when perpendicular lines are created by 2 lines that intersect. More specifically, they intersect and form right angles. And we have a special symbol for when we are marking things as perpendicular. And what that looks like is kind of like an upside down T. Okay. And we can also have perpendicular lines. This definition also applies to rays and segments. So we could say my segment AB is perpendicular to, I'll use line XY. So even if you're not given a diagram, now you should be able to translate this sentence I just gave you into a picture if you needed to draw it. So I know it's segment AB and a line XY. So remember, your segment should have endpoints. X and Y are just points on a line. And you could go even further, since now you know they're perpendicular, you could also mark a right angle. And we use that box notation or box in our figure to denote a right angle. So we have 3 theorems that go along with our perpendicular lines. And our first one says, if 2 lines are perpendicular, then they form congruent adjacent angles. So we are actually going to do the proof for this because remember, theorems require proof, postulates do not. So here's my given information. I'm going to have 2 lines, L and N, and they're going to be perpendicular. And we are going to prove, and we'll draw a diagram in a second, but we're going to prove that angles 1, 2, 3, and 4 are all congruent. And here's the figure we're going to work with. So here's my line L. Going across will be my line N. And my 4 angles, 1, 2, 3, 4. And when you look at our picture, start thinking about how you would go about proving this. We've been getting some proof practice here. I'll set you up a little bit in that there are, I think we can do this in 3 steps, where the first step is L is perpendicular to N. And my last step is what I'm trying to prove. Angle 1 is congruent to angle 2, angle 3, and angle 4. So using that information, think about our justifications and what's the middle step that's missing. How do we know that they're all congruent angles? I know my first justification is given to me. And that middle step, I have to come up with some sort of reason that would say all my angles are equal. Well, from my definition that we just wrote, I know they're forming right angles if the lines are perpendicular. So my step 2 could be that angle 1, 2, angle 3, and angle 4 are all 90 degrees. And that, again, comes from my definition of perpendicular lines. The definition says that they're forming right angles, and I know all my right angles are 90 degrees. And once I know they all have the same measurement, I know they're congruent because that's the definition of congruent angles. And that's the whole proof. So one new thing for our theorems and proofs, when we're finished with a proof, what you'll often see and what we're going to be doing is at the end we have Q, E, D, or you can include just a box. And it's kind of like one big period, like we've done it, this is our theorem, and we proved what we set out to prove. Our second theorem says if two lines form congruent adjacent angles, then the lines are perpendicular. Now, if I show you these two theorems back to back and you reread them, how is theorem 2.5 related to theorem 2.4? So this theorem is actually the converse of what we just proved. So this time we are going to start with our angles and work backwards to prove that the lines are perpendicular. In this diagram, I'm going to use my lines L and N again, and I'm only going to label two angles because I think that's all I need. And my given information will be that angle 1 is congruent to angle 2, okay, because we're starting with congruent adjacent angles. We are going to prove line L is perpendicular to line N. Now this one requires more steps than the last one, but here's how we'll get ourselves started. Start with our given information, so angle 1 congruent to angle 2, and I'm actually even going to change this a little bit and just say that the measure of angle 1 equals the measure of angle 2. And that's still given to me. The difference between these two things, congruent talks about the actual shape of the angle, like the same size, same shape, whereas my second piece here with the equal sign talks about the actual angle measure. That's why I put the M's for the measure. So this is talking specifically about the units. And the reason I want to do that is because in my second step, I'm going to set up an equation where I say that the measure of angle 1 plus the measure of angle 2 equals 180. And to justify that, I'm using my angle addition postulate. Remember, the angle addition postulate says that if two angles are next to each other, we can add them together for one big angle. And because angle 1 and 2 sit on a line together, I know they're a straight angle pair, so they equal 180. And now I'm ready to substitute. So there's my justification, substitution. I'm going to switch out either angle 1 or angle 2, and I'm going to say the measure of angle 1 plus another angle 1 equals 180. And I'm actually going to simplify this on this step. And remember, simplifying does not require a different justification. Now I'm ready to say that the measure of angle 1 equals 90 because I divided. So I use my division property, which means the measure of angle 2 also has to be 90 because 1 and 2 are equal. So again, substitution. And now that I have two equal 90-degree angles, I know that L is perpendicular to N. by the definition of perpendicular lines. I had to be able to show that my two angles were 90 degrees though before I could use my definition. And our last theorem says that if the exterior sides of two adjacent acute angles are perpendicular, then the angles are complementary. And this theorem you are actually going to prove in your homework and practice tonight. It is a problem in our textbook, so it'll get you set up a little bit. And what this looks like, I'll at least give you the diagram here to work with, is we are talking about adjacent acute angles. So first draw yourself adjacent acute angles. And I'm going to label this as A. My vertex will be O. And I got B and C. So it says that if the exterior sides, so in this case, my AO and OC, if those two sides are perpendicular, then those two angles must be complementary. So again, this will be part of your homework. It's partially set up for you in the work, so you just have to provide a couple of the steps for justifications and a couple of the statements. Right now, what I want you to try for is these true and false problems. And these I'm going to have pop up as questions in the Edpuzzle. So think about your answers, and then I'm going to have you submit your answers for the Edpuzzle. And before we move on, I'll give you a quick recap of our answers. So we know we're given, this given statement was important. AB is perpendicular to CD. So that gives me these four right angles. Okay. And then here is a quick answer key for you if you want to kind of check how you did. The first answer would be false. AB perpendicular to EF. We don't have anything that supports that. CGB is a right angle. That was true. CGA is a right angle. Also true. DGB equals 90. Also true. EGC and EGA. So I'm going to mark these on my EGC, this little angle, and EGA, this big angle, are complements. Also true. They add up to that 90-degree angle we have created by our lines. DGF is complementary to DGA, false, and EGA complementary to DGF, true. Your next little practice section here, we are going to draw another diagram to help us. And we have this given information about our lines up here we want to work with. So anytime you're not given a picture, draw yourself one. It's going to be much easier to work through the problem if you have something to look at. So here's what our diagram is going to look like. I made my line a little too big, I guess. We got point A over here, B in the middle, C. I'm going to draw another ray, BF. BE is my line going up, and off to the side here will be ray BD. So in the first row going across, your angle measures are all going to have a numerical answer working from the 40. in your second row of answers, these are going to look more like expressions. So for example, I'm going to do CBF. If I know this is 40 degrees, and using my given information here, I know I have a right angle. That means EBF has to be 50. And the way I did that will help me answer for my second row. I did 90 minus X, 90 minus this angle measure. So that's what your answers are going to look like as you fill these in. I'm going to ask you a couple of these in the Edpuzzle. So work through the chart and then read the questions and be careful for which angle measure I ask you for. Just to fill in going across, you should have had 40, 50, and 130. And then this would also be X, another 90 minus X, and this one 90 plus X.